we continue our discussion on the composition of the complex ions. Yesterday I had explained to you a little bit. Essentially I was telling you that there is method of continuous variation, mole ratio method and slope ratio method. So, in the method of continuous variation, I had explained to you that we get a curve something similar to what we had seen earlier, this figure. You end up with a figure something like this. You take a known molar concentration of the metal ion and then keep on adding the reagent in the same molar concentration, and wherever you get different inflection point, that would be the composition of the complex. So, if you get if you start with 1 molar substance and the inflection point is at 1 molar volume of the titrant, then it is 1:1 complex. So, if it is 1:2 complex, the inflection point would shift to 0.66 or something like that. So, depending upon the mole ratio, you will get the composition of the complex. Now, the other methods is the mole ratio method. Here what I do is I take the reagent 100% and metal 0%. Okay. So, here Vm is 0% and Vm by Vl I compute and I keep on increasing from 0, 0.2, 0.4, 0.6, 0.8, 0.1. Since it is a ratio, maximum is 1 only. So, if I take 100% of the reagent Vl, Vl refers to ligand. If I take 100% of the ligand, there is no metal and no complex formation. As I increase this to 2% and Vl is 8%, 80%, the mole ratio what I get is 0.2. So, I get some amount of complex will be formed, but unless it is optimum I will not get a inflection point. So, I keep on increasing 0.2, 0.4, 0.6, 0.810. Similarly, I can do for the ligand. When the Vm is 0, Vl would be 1, and when Vm is 0.2, this would be 0.8, something like that. So, if I plot the absorbance versus the mole ratio at the inflection point, I calculate where is this. So, suppose my Vm is 0.33, it automatically fixes the Vl concentration to 0.66. That means it is 1:2 ratio. Suppose it is 0.5, the inflection would be somewhere here, 1:1 complex at 0.5. And then similarly, if it is 1:3, you can calculate where the inflection point would be coming, and we can always determine using this method. This is a very well known method, and this complex Jobs ratio method is a very well known and foolproof method. Then there is another slope. This is essentially same thing what I had told you, more continuous mole ratio method. Here moles per ligand per cation. So, 1:1 if I have an inflection point, and here it would be 1:2. If the inflection point occurs somewhere here, then it would be 1:3, something like that. You can have ligands combining up to 1:6 ratio also, octahedral complexes. So, this is a very simple straightforward method, and the slope ratio method I will not explain to you, it is given in regular textbooks. What I would like to do is I will give you an assignment based on the slope, how to determine the slope composition of a complex using the slope ratio method, which I had indicated here. This I will not be explaining to you, but it will be some sort of an assignment for you. Okay. So, another application, we move on to another application of the spectrophotometry. Nowadays, since 1980s, I wanted to explain to you this nowadays since 1980s there are continuous requirements of measurements of the pollutants and things like that, and whenever an industry is letting out an effluent, then it is required that the effluent be monitored continuously, not regularly, and not at regular intervals. So, if it is a continuous, there has been a tremendous demand for continuous monitoring methods. Even in India, since last 1 year, Central Pollution Control Board has mandated that almost all the industries must monitor the effluents on a continuous basis, and this could be electrochemical method, or it could be spectrophotometric method, or it could be any other method suitable for a particular pollutant. But whenever metal ions are involved and BOD and COD and several other pollutants are involved, it is important that a spectrophotometric method provides you a very cost effective method even for continuous analysis. So, this is something a slight modification of a spectrophotometer. What you will be doing is you will be creating a manifold. I run a continuous stream of a reagent, and then I create a manifold, and here the sample will be coming. Here I can add a reagent. This is reagent. This is the sample. Oh, the reagent I have already here. Sample, that is the effluent, and here I can add reagent. I can say reagent 1 and reagent 2. This could be an organic reagent, this could be a buffer, and all these things will mix, and then I have a continuous stream flowing out. This is the colored complex. This whole unit, this unit is mounted in the optical path of the spectrophotometer. Located in the stream or nearby. Normally what people do is, if I have an effluent stream, this will be going for treatment. Okay, and I take a small sample out of this and then connect it to the sample here. Connect it to here. So, this is the type of arrangement we normally look for in a spectrophotometer whenever we want to do the sample analysis. Generally what happens is, you can even take a small sample from a syringe and then inject it here, inject it in the manifold. So, you can inject it through this sample or this port reagent. Reagent 1 and reagent 2 will be flowing continuously, and the sample can be injected and measured. Whenever there is no reagent, it will be acting as a reference solution, and whenever there is a reagent, there will be given a certain amount of time, you will be getting a color complex. So, in a continuous flow injection analysis, the curve of absorbance versus time would show a reference, and then complex will form, and then as it is swept out of the system, this is out. As it is swept out of the system, the color will come down, and then it will again reach the reference level. So, this is known as flow injection analysis. This flow injection analysis, abbreviated as FIA. There are several spectrophotometric manufacturers who will give you a manifold made of Teflon and other things, which will give you accessibility for flow injection analysis. So, basically what it involves is that the measured amount of small amount of liquid is moved into a non-segmented stream of the reagent, and as the injected sample and reagent carrier proceeds down the narrow tube into the manifold, the reagents are pumped and the normal color complex formation takes place, but this takes place under dynamic flow conditions. That means, it passes through a flow cell attached to the spectrophotometer continuously. So, the sharp signal develops, followed by a trailing edge, just like what I showed you earlier. Okay. The peak height, in this case, the peak height is proportional to the concentration of the analyte. The sample peak can be detected in about 15 seconds after the injection. This much of time delay you can always give whenever you are operating a machine in flow injection mode. Since the system operates under dynamic conditions, the sample clears out of the reactor in about 15 seconds and be ready for another injection. Okay. So, the whole system can be made very compact, and samples as small as 30 microliter of the sample and reagent volumes of less than 1 ml normally are possible to use. Normally in a spectrophotometer, we expect the sample to be of minimum size of about 5 ml for normal 1 centimeter cells, and of course, smaller volumes if the path length is less, and higher volumes if the path length is more. But in FIA, we handle samples as small as 30 microliters, and total reagent volume itself would be approximately 1 ml. So, we move on to another application of spectrophotometer. This is known as turbidimetry and NEPHLOMETRY. Basically, a spectrophotometer measures the color. So, one of the preconditions for a spectrophotometer measurement for a spectrophotometric measurement is that the solution must be absolutely free from turbidence. In the initial stages, when I was teaching you about the spectrophotometry, I had written that the fate of the electromagnetic radiation is the sum of radiation absorbed, some of it is transmitted, some of it is scattered, some of it is reflected, some of it is refracted, like that. And it is not I had not written turbidimetry, okay, turbid solutions, but basically a turbid solution means it is an interferent or the sample is in the form of a precipitate. Now, Beer-Lambert's law does not apply to turbid solutions. Okay. Now, you will come across real life situations where turbidity is part and parcel of our life. For example, the precipitation of barium sulphate and silver chloride, all these substances precipitate whenever there is chloride in solution. So, can precipitation titrase reactions be made part of spectrophotometric arsenal? The idea is, if I can make the precipitate in a reproducible manner and make it stable, all other variables being constant, if the precipitate is having a specific color, then I should be able to determine the precipitate, the sample in the form of a precipitate itself or as a turbid solution itself, provided I do not have any other variables. Even though this is a violation of Beer-Lambert's law, empirically I can make it work like this. So, the conditions for such a precipitation reaction would be that the precipitate should be in the form of a very fine powder. It should not be colloidal, of course, because the colloids do not settle, but precipitates do settle. That is the main difference between the colloids and precipitation. And sometimes for colloids also we have the same title is given NEPHLOMETRY, and we will come to that in a minute. So, the basic idea is to have a very small concentration of the precipitate in the form of a suspension, so that the suspension does not settle down. It should not. If it settles down, your absorbance value will be wrong. Okay. So, it may be scattered or it may not be scattered, it may be just transmitted, etc. But still, if the precipitate is held in solution without much movement, then I can get an empirical correlation of the absorbance versus concentration. So, if such a thing is possible, then I can go ahead with the determination of the analyte in the form of a precipitate itself. So, this opens up a large number of chemical reactions which can be made amenable to spectrophotometric determination. So, the scope of spectrophotometry can be greatly enhanced, expanded, if the optical inhomogeneity in a sample can be reproducibly measured. So, the basic idea is the presence of suspended matter in stable systems and thermal density fluctuations. Temperature is a big parameter in this, and colloidal particles, all these things introduce optical inhomogeneity in an otherwise homogeneous medium that results in inelastic scattering. So, inelastic scattering means measured at the same wavelength. Elastic scattering means measured at different wavelengths. So, the scattered radiation is preferably absorbed rather than transmitted through the sample. So, in turbidimetry you can make the measurements as absorbance but not as transmittance. This is a major difference with respect to spectrophotometry. In spectrophotometry we can either make the measurement either as absorbance or transmittance, whereas in turbidimetry we will make the measurement preferentially as absorbance. Okay. So, the intensity of the parallel and perpendicularly polarized components of the electromagnetic radiation is a function of the is a basic function of the relative refractive index. This we have seen earlier, but it is also a function of the size of the particle if we are making any turbidimetric measurements. So, the angle of observation, that is also important with respect to precipitates, because many of the precipitates are not in the form of spherical shape. They may be conical, they may be square, they may be hexagonal, and so many other types. So, the angle of observation relative to the incident radiation is also an important factor, and the concentration of the scatterer, that is the precipitate, is also some sort of a factor for the linearity of the concentration. So, basically the size parameter, if we assume that it is of spherical shape, then I can say this alpha is equal to 2 pi r upon lambda. This is size parameter, determines the phase distribution of the scattered radiation. Okay. So, the scattering envelope is symmetrical when the size parameter is smaller than 1/10 of the wavelength. This is very important concept. That means, if the size parameter is 1/10 of the wavelength of the size, basically wavelength is also a type of a measurement of length. Okay. So, if it is 1/10 of that size and the refractive index of the particle is almost same as that of the surrounding medium, that is Rayleigh scattering. So, we have a very nice measurement possible. As the size parameter reaches 1/4 of the wavelength, suppose the particles aggregate and then coagulate, then the particle size becomes bigger and bigger. So, as the size parameter reaches approximately 1/4 of the wavelength of the incident radiation, that is, I choose the incident radiation using a monochromator now. So, the monochromator, if I choose a particular wavelength, I know what is the size of the radiation. So, the scattering is, if it reaches in about 1/4, then the scattering is concentrated only in the forward direction. This is very important, because I am going to measure the turbidence only in the forward reaction, that is a forward direction. So, it is not measured in all the directions, only along the direction of the electromagnetic radiation. So, if the particles are larger than the wavelength of the incident radiation, scattering will be obviously through in all directions, and scattering intensity would also be a very complex function of the angle of scattering, but still a large amount of it is scattered in the forward direction only. Still we can make the turbidimetric measurements even if the particles are larger. This is a very gratifying factor, because this opens up the determination of almost all types of particles, precipitates, for spectrophotometric determination. This is known as me-scattering. Okay. So, me-scattering permits one to use the turbidimetry as a monitoring method, provided the precipitates are colored and scatter in the UV visible region. So, for very large particles, suppose they really concentrate and do not move around, the scattering does not depend on the wavelength. Basically, of course, it has no meaning for very large particles, because they may block the radiation also. So, scattering does not depend upon the wavelength, but depends upon the particle geometry. So, if it is round shaped, square shape, etc., cubical, then it also depends upon the molecular absorption and then sample concentration, the particle size distribution, because we know that from experience that most of the chemical reactions produce a precipitate varying in size. They are not always of the same size. So, the size distribution also becomes very important in most of the turbidimetric measurements, and sometimes even in the physical design of the instrument used for measure, that is sample compartment. Physical design of the instrument means sample compartment, it is used for measurement. Therefore, the results are in any case 100% in and chemical turbidimetric methods, they are always empirical. This we have to understand very clearly, that it is not very easy to correlate the absorbance values to Beer-Lambert's law or any other known laws, and they exhibit variance in the data even though the same calibration standard is used. Suppose you use a precipitation standard today and tomorrow you make the same precipitation, another one more reaction, make the same measurement, again it will show you a different absorbance, but within certain limits. So, this is the catch in all spectrophotometric reagents of using turbidimetry, because the results are essentially empirical. There is no guarantee that you may get the same absorbance every time. So, there are two methods for measuring the turbidity of a sample in the same axis and also perpendicular to the incident radiation. So, when measurements are performed in the forward direction, just like spectrophotometry, that is in the direction of electromagnetic radiation, analogous to similar to absorbance, it is called turbidimetry. But suppose I measure the absorbance at right angles to the direction of the incident beam, it is called NEPHLOMETRY.